Hello there, and welcome back to the gentle whispers of Sleepy Wiki. As you settle in, perhaps you can let your shoulders soften, releasing any tension you might be holding. Feel your breath flow in and slowly out, a peaceful rhythm, allowing your mind to quiet itself. Tonight, we turn our gaze not just to the stars, but to the profound, quiet question they hold within their ancient, shimmering light. Are we alone? We'll drift through the concept of astrobiology, a field that dreams of life beyond our pale blue dot, pondering the very conditions that allow existence to bloom in the cosmic garden. Imagine tiny microbial worlds stirring on distant moons, or the silent dance of intricate chemistry patiently coming to life on planets far, far away. It's a journey into the deep time of the universe and the subtle possibilities of emergence, an exploration of how life, in its myriad forms, might gently weave itself into the boundless fabric of the cosmos. There's no rush, just quiet contemplation as we wander this fascinating thought. If these quiet wanderings bring you a sense of peace, a gentle tap on the like button or subscribing to our channel helps these sleepy journeys find others who might need a moment of calm, drifting softly to sleep. Now let us very gently begin to unfurl the story of astrobiology and perhaps, with it, drift a little closer to rest. Imagine the universe in its infancy, a vast, quiet nursery shortly after its fiery birth. For countless eons, it was a place of sublime simplicity, a primordial soup, deep and boundless, composed almost entirely of the lightest elements, hydrogen and helium. These cosmic pioneers, making up over 98% of all matter, formed immense shimmering gas clouds, patiently waiting to be painted with richer hues. But simplicity, while beautiful, held little promise for the vibrant, complex tapestry of life. For life, in all its astonishing forms, requires a much more diverse palette, a richer array of fundamental building blocks than just hydrogen and helium. It needed elements like carbon, oxygen, nitrogen, the very atoms that make up our bodies, our breath, our minds. And so, the universe began to forge its own tools, its own master alchemists, the stars. From the gentle gravitational collapse of those vast hydrogen and helium clouds, the first stars were born, igniting spectacularly. Within their fiery hearts, under immense pressures and temperatures, a miraculous transformation began. These stars became luminous furnaces, where hydrogen atoms, driven by gravity, squeezed together, fusing to create helium. This process, nuclear fusion, released the energy that allowed stars to shine, becoming the cosmos's first quiet kitchens. But this was just the beginning of their cosmic culinary adventure. As stars aged, particularly the most massive ones, their core temperatures soared even higher. Once their hydrogen fuel began to wane, the stars contracted, growing hotter still. The helium itself became fuel, fusing in turn to create carbon, the very backbone of organic chemistry, the crucial element allowing for the long, complex chains of molecules upon which life depends. From carbon, further reactions yielded oxygen, nitrogen, neon, magnesium, silicon, sulfur, and all the way to iron. Each heavier element, a new brush stroke on the canvas, a new note in the cosmic symphony, slowly enriching the once simple universe. Yet, Even the mighty stars are not eternal. For some, particularly those behemoths many times the mass of our own sun, their magnificent lives conclude not in a gentle fading, but in an event so spectacular, so profoundly powerful, a supernova. Imagine a star, having exhausted its nuclear fuel, collapsing under its own immense gravity in mere seconds, only to rebound with an explosive force that can briefly outshine an entire galaxy. These aren't merely cosmic fireworks, they are the universe's ultimate foundries. It's during these blinding flashes in temperatures and pressures unsurpassed anywhere else in the cosmos that the heaviest elements are forged. Elements like gold, silver, platinum, and uranium, substances we cherish, are created in a fleeting moment through rapid neutron capture. And just as importantly, these explosions don't simply create, they scatter. They become the universe's great cosmic gardeners, seeding the vast emptiness between the stars with a rich, fertile dust of newly minted elements, along with the lighter elements formed during the star's previous life phases. Even less massive stars, in their serene final stages, gently cast off their outer layers as beautiful planetary nebulae, further enriching the interstellar medium with freshly brewed carbon, nitrogen, and oxygen. The interstellar medium itself, this vast expanse of gas and dust between stellar systems, becomes the cosmic mixing bowl. It's here, in these quiet, cold clouds, that the stardust, the very atoms fashioned in distant stars and scattered by their dying breaths, mingles, combines, and waits. It's in these regions that the stage is set for new generations of stars, and critically, for planets to form, carrying within them the potential for life. Now, consider life as a beautifully complex recipe, and the universe as a master chef gathering just the right ingredients. For life as we understand it, a very specific combination of these cosmic ingredients is essential. Think of the carbon atom first. Imagine it as a tiny, eager connector, a versatile Lego piece with 4 little arms, ready to link up with other atoms. Its unique ability to form long, stable chains and intricate rings makes it the indispensable architect of organic molecules, the very skeleton of sugars, fats, proteins, and DNA. Then there's hydrogen, the most abundant element, humble yet essential. It forms the structure of water, the universal solvent, and is a key component of virtually every organic molecule. Oxygen, a bustling, energetic atom, is vital. It's not only part of the water that makes up so much of us, but also crucial for metabolic processes that extract energy from food, fueling nearly all complex life on Earth. Nitrogen, a quieter but crucial component, forms the rings within our DNA and RNA, the very blueprints of life, and builds the amino acids that create proteins, the tireless workers performing nearly all cellular functions. Phosphorus, the silent architect, forms the sturdy backbone of DNA and RNA molecules, providing structural integrity. It also forms energy packets, like tiny rechargeable batteries, that power nearly every cellular process, such as ATP. Finally, sulfur, a subtle but strong builder, helps to give proteins their unique three-dimensional shapes. These specific shapes are critical, determining how proteins function ensuring they can perform their diverse tasks, from catalyzing reactions to providing structural support. These 6 elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, CHNOPS, are the primary building blocks, the cosmic alphabet from which all known life is written. But ingredients alone are not enough. They need a medium to interact, a universal solvent, a cosmic cradle. And that, dear listener, is where water enters the scene. Formed from hydrogen and oxygen, water's unique properties, like its ability to dissolve many substances and its broad liquid temperature range, make it the ideal environment for the intricate chemical reactions necessary for life to unfold. Beyond these core 6, a supporting cast of trace elements plays vital roles. Iron for carrying oxygen in our blood and energy production, magnesium for capturing sunlight in plants, calcium for strong bones and nerve impulses, and sodium and potassium for the electrical signals that race through our brains. Each is a tiny cog, indispensable in the grand machinery of life. So, as you lie quietly, consider this wondrous thought. Every atom of carbon in your cells, every speck of oxygen you breathe, every strand of nitrogen in your DNA, they all have a story. They were once part of a distant star, forged in its fiery heart, or perhaps created in the blinding flash of a supernova explosion billions of years ago. You are, quite literally, stardust walking, a living, breathing testament to the universe's incredible ability to take simple beginnings and, through eons of cosmic alchemy, produce something as intricate and conscious as you. But how do these scattered cosmic ingredients, these particles of stardust and cosmic gas, eventually gather together to form rocky planets, worlds where they might find the perfect conditions to begin their long journey towards the very first stirrings of life? Let us turn our gaze now not outwards to distant worlds, but inwards, to our very own cradle, Earth, billions of years ago. Imagine, if you will, a world very different from the one we know today, a young, restless planet, still finding its rhythm. Picture it. 4 billion years ago, a time when Earth was a bustling, tumultuous infant. The skies above were often dark, not with clouds as we know them, but with volcanic ash, a constant reminder of the fiery heart beating beneath its crust. There was no gentle blue atmosphere filled with oxygen, no widespread forests humming with life. Instead, the air was thick with gases like methane, ammonia, water vapor, and carbon dioxide, exhaled by countless volcanoes that dotted the landscape like glowing embers in a vast, dark forge. Beneath these turbulent skies, vast oceans stretched, warm and often shallow, shimmering under a sun whose rays, unobstructed by an ozone layer, delivered intense ultraviolet light. This early Earth was a place of immense energy. Lightning storms frequently rent the sky, powerful bolts crackling through the dense atmosphere, striking the oceans and land. Geothermal vents, deep in the ocean floor, spewed forth superheated mineral-rich water, creating scorching hot chimneys that pulsed with chemical activity. This was our planet's fiery, dynamic beginning, a primordial crucible where the most extraordinary journey of all was about to begin. It was within this restless, energetic environment that scientists began to ponder one of the greatest questions. How did life, this intricate dance of chemistry and consciousness, first emerge from mere non-living matter? This grand question is what we call abiogenesis, the birth of life from non-life. It's not creation in the sense of a sudden snap of fingers, but rather a slow, patient, molecular ballet that unfolded over millions of years. Think of early Earth's oceans as a colossal cosmic kitchen, brimming with the most basic ingredients. The gases in the atmosphere, dissolved into the warm waters, provided simple inorganic molecules. For decades, scientists like Alexander Oparin and J.B.S. Haldane proposed that these conditions could have fostered a primordial soup, a rich broth of dissolved chemicals where the ingredients for life might slowly assemble. How could such a soup begin to simmer? The energy sources we spoke of earlier, the fierce lightning, the intense ultraviolet radiation from the sun, and the searing heat from volcanic activity and hydrothermal vents, these were the sparks, the catalysts. They provided the necessary kick for simple atoms and molecules to rearrange themselves into something more complex. One of the most iconic demonstrations of this idea came in the 1950s, with the brilliant experiment by Stanley Miller and Harold Urey. They built a sealed apparatus, a miniature early Earth in a flask. They filled it with the gases believed to be present in the primordial atmosphere: methane, ammonia, hydrogen, and water vapor, then heated the water to simulate oceans and sent electrical sparks through the gas mixture to mimic lightning. After just a week, they looked inside their miniature world. And what did they find? A reddish-brown sludge at the bottom of the flask. Within that sludge, they identified amino acids, the very building blocks of proteins, which are essential for all life we know. This was a monumental discovery. It showed that the basic components of life could spontaneously form under early Earth conditions. It was like discovering that simply mixing flour, water, and yeast with a bit of heat could miraculously produce dough, ready for baking. The Miller-Urey experiment and subsequent similar experiments have shown that not just amino acids, but also nucleotides, the building blocks of DNA and RNA, and simple sugars could arise spontaneously. Even deep-sea hydrothermal vents, with their unique chemistry and temperature gradients, are now considered powerful incubators for these early organic molecules, perhaps even more so than surface ponds, offering a protected environment away from harsh UV radiation. But life isn't just about having individual building blocks, like scattered Lego pieces. It's about assembling them into intricate structures, like a magnificent Lego castle. The next grand challenge for abiogenesis was understanding how these simple organic molecules, these monomers, could link up to form long, complex chains called polymers. Think of amino acids linking into proteins or nucleotides linking into strands of RNA. This step posed a peculiar problem. Forming these links, called polymerization, often requires energy and typically happens more readily in dry conditions. But early Earth was awash in water, and water tends to break these bonds apart. So, how did these molecular chains form? Here, scientists have proposed several ingenious solutions. Imagine shallow tide pools or volcanic vents that might experience cycles of wetting and drying. As water evaporates, the concentration of these precious organic molecules would increase, pressing them closer together, and perhaps, with a gentle surge of energy from the sun's warmth or a nearby vent, they could link up. Think of a bustling marketplace where ingredients are brought together, and then, as the crowds thin, the skilled artisans begin to weave them into elaborate tapestries. Another fascinating idea involves humble clay minerals, like montmorillonite. These clays have a unique layered structure that can act like a scaffolding, providing surfaces where organic molecules can concentrate, stick, and then link up more easily. Clay can even catalyze or speed up these reactions, like a friendly matchmaker bringing molecules together to form enduring bonds. Deeper in the ocean, the mineral surfaces around hydrothermal vents could also have played a similar catalytic role, providing sheltered nurseries for these fledgling molecular assemblies. Among these newly formed polymers, one molecule stands out as particularly special in the story of life's origin: RNA. While today, DNA is the celebrated keeper of our genetic blueprint, scientists now widely believe that RNA, or something very much like it, was the original star of the show. This is the heart of the RNA world hypothesis. Why RNA? Because RNA is a true molecular shapeshifter. Unlike DNA, which is primarily a stable information storage molecule, RNA can do so much more. It can store genetic information, much like DNA, but it can also fold into complex, three-dimensional shapes and act like an enzyme, catalyzing chemical reactions. These catalytic RNAs are called ribozymes. Imagine a tool that can both hold a blueprint and also build the structure itself. RNA could be both the recipe and the chef. In the RNA world, early RNA molecules could have replicated themselves, not perfectly but well enough, using other RNA molecules as templates. This simple, imperfect self-replication, driven by the principles of chemistry and fueled by the energy of early Earth, allowed for variation, and with variation, the gentle hand of natural selection could begin its work, favoring molecules that were slightly better at copying themselves or at catalyzing useful reactions. But even the most clever self-replicating molecules need a home, a protected space. Imagine a tiny, delicate chemical factory bustling with activity. It needs walls to keep its precious contents together, to concentrate its reactions, and to separate its internal world from the chaotic outside. This brings us to the formation of protocells. Simple fatty acids, which could also have formed spontaneously on early Earth, possess a marvelous property. In water, they naturally arrange themselves into spherical bubbles called vesicles or liposomes. These are like microscopic soap bubbles with a double-layered membrane that encloses a tiny aqueous space. These early membranes would have provided the crucial boundary, a semi-permeable skin that could concentrate the precious organic molecules and nascent RNA within, protecting them from the turbulent external environment. They allowed some things to come in and some things to go out, but maintained a distinct internal environment. These protocells weren't truly alive in the way we understand life today, but they were the crucial precursors. They could grow by incorporating more lipids from their surroundings, and they could even divide, pinching off into smaller daughter vesicles, carrying some of their internal contents with them. This was the nascent flicker of independent existence, the very first step towards individual organisms. Over vast stretches of time, perhaps hundreds of millions of years, these protocells, containing their evolving RNA molecules, would have gradually become more sophisticated. The RNA might have eventually given way to the more stable DNA for genetic storage, and the complex machinery of protein synthesis would have emerged, allowing for a much wider array of catalytic functions. This long, slow refinement would eventually lead to the last universal common ancestor, or LUCA, not the first life, but the ancestor from which all existing life on Earth descended. The story of abiogenesis is one of the most compelling scientific quests, a deep dive into the very fabric of existence. It's a puzzle with many pieces still scattered, but with each new discovery, the picture of life's incredible journey from simple chemistry to complex biology becomes clearer, like watching a forgotten photograph slowly develop in a dark room. It reminds us of the profound capabilities of matter itself, given enough time, energy, and the right conditions. As we ponder this magnificent, slow dance of molecules leading to the first whispers of life on our own planet, we naturally wonder, could similar dances have played out on other worlds, under different skies and in different waters? Where else might such a delicate dance of life unfold? Our own Earth, vibrant and teeming, holds a precious secret within its very being, the shimmering, life-giving presence of liquid water. It's a fundamental ingredient for all known life, a cosmic elixir that allows cells to grow, nutrients to dissolve, and countless biological processes to unfurl. But for water to remain in its liquid state, not frozen solid like an endless winter, nor boiled away into a thin, ghostly vapor, a planet must exist within a very particular, very special cosmic neighborhood. Imagine, if you will, a cozy campfire flickering softly in the deep night. If you sit too close, the heat becomes unbearable, the flames too fierce. If you wander too far, the warmth fades and the chill of the night creeps in. There's a just right distance, isn't there, where the heat is comforting and inviting? Planets, too, have such a just right distance from their parent star. We call this exquisite region the Habitable zone. It's a celestial Goldilocks zone, where the temperature on a planet's surface, assuming it has a suitable atmosphere, might be just right for liquid water to pool in lakes and oceans. Not too hot, where water evaporates into a steamy oblivion, leaving behind a parched, desolate world like a forgotten desert. And not too cold, where water locks itself away in an icy embrace, forming a frozen, unyielding landscape, much like the distant, frosty moons of our own outer solar system. This habitable zone isn't a fixed, universal boundary. It's a dynamic, shimmering band that changes with the star at its heart. A large, blazing blue star, fiercely hot and luminous, will push its habitable zone far outwards, like a giant, roaring bonfire whose comforting warmth reaches across a wide meadow. But such stars burn brightly and briefly, their lives a spectacular flash in the cosmic pan. Then there are the smaller, cooler stars known as M dwarfs, which are far more common than our sun. These gentle crimson embers have a habitable zone that snuggles much closer to their stellar warmth, like a tiny glowing hearth. A planet orbiting such a star might be tidally locked, always presenting the same face to its sun, with one side perpetually day and the other eternally night, creating entirely new climatic challenges and opportunities for life. For decades, this Goldilocks zone remained a theoretical whisper, a beautiful concept in the minds of astronomers. But how do we find these potential havens? How do we locate worlds, perhaps even rocky worlds, nestled within these precious cosmic bands? This is where the thrilling quest for exoplanet discovery begins. The search for planets beyond our own solar system. Imagine looking for a firefly dancing around a distant lighthouse, trying to see the tiny insect against the brilliant glare. That's a bit like trying to find an exoplanet. Stars are incredibly bright, vast, and far away, while they're orbiting. Planets are infinitesimally small, dim, and often swallowed by the star's overpowering light. It's an astronomical game of hide and seek, requiring ingenious methods and incredible technological precision. One of the most successful ways we've found these hidden worlds is called the flourish or transit method. Picture a star, a brilliant beacon of light shining steadily across the cosmos. Now, imagine a tiny moth, unseen to the naked eye, fluttering directly in front of that lighthouse from your distant vantage point. For a fleeting moment, a minuscule fraction of the lighthouse's beam is blocked. You wouldn't see the moth itself, but you would notice a tiny, almost imperceptible dip in the light's steady glow. That, dear listener, is precisely what happens with the transit method. When an exoplanet passes directly between its star and our telescopes here on Earth, it causes a faint, temporary dimming of the star's light. It's like a cosmic eclipse in miniature, a fleeting wink from a distant sun. By meticulously measuring this dip in brightness and by observing it repeat at regular intervals, we can deduce a wealth of information. The amount of dimming tells us the size of the planet relative to its star, and the regularity of the dips reveals its orbital period, how long it takes to complete one journey around its sun. Missions like the legendary Kepler Space Telescope and the current TESS, Transiting Exoplanet Survey Satellite, have been masters of this delicate art, patiently watching hundreds of thousands of stars for these telltale winks, revealing thousands of hidden worlds. Another powerful technique we employ is the radial velocity method, sometimes called the Doppler wobble method. This approach doesn't rely on a planet crossing in front of its star, but rather on the gravitational dance between the two celestial bodies. You see, a star doesn't just sit perfectly still while its planets orbit it. Instead, the planet's gravity exerts a subtle but constant tug on the star, causing the star itself to wobble ever so slightly, like a giant ballroom dancer being gently pulled by its much smaller partner. It's a cosmic tug-of-war, with both objects revolving around a common center of mass. We can't usually see this wobble directly, but we can detect its effect on the star's light. As the star wobbles towards us, its light waves are compressed, shifting towards the blue end of the spectrum, a phenomenon known as blue shift. As it wobbles away, its light waves are stretched, shifting towards the red end of the spectrum, red shift. By carefully measuring these tiny rhythmic shifts in the star's spectral lines, Like listening to the gentle murmur of a celestial pendulum, we can infer the presence of an unseen planet and even estimate its mass. A heavier planet will cause a more pronounced wobble, while a lighter one will only cause a faint tremor. These incredible techniques, along with others like direct imaging, which is like trying to photograph that firefly next to the lighthouse by perfectly blocking out the lighthouse's beam, and gravitational microlensing, where a star and its planet act like a cosmic magnifying glass, bending the light from a background star, have transformed our understanding of the universe. We've discovered thousands upon thousands of exoplanets, worlds of all shapes and sizes, from scorching hot Jupiters to mysterious super-Earths, some even within the very habitable zones we just explored. Each new discovery is a testament to our insatiable curiosity, a tiny step closer to answering humanity's most profound question: are we alone? The detection of these worlds, some potentially ocean-bearing, others rocky and Earth-sized, fuels our imagination and pushes the boundaries of scientific exploration. But finding them is just the first whisper in a much longer conversation. Each new discovery fuels our imagination and pushes the boundaries of scientific exploration, bringing us closer to answering humanity's most profound question: are we alone? To answer that question, we must first understand what life truly needs to thrive. We tend to imagine creatures much like ourselves, bathed in sunlight, breathing air, sipping fresh water. But what if the universe holds a far grander, more resilient tapestry of life than we've ever dared to dream? On our very own planet, beneath layers of ice, deep within scalding vents, and across parched, ancient lands, there exists a secret world, a testament to life's extraordinary tenacity, the world of extremophiles. Imagine for a moment a creature that calls a boiling hot spring its gentle home, a place where temperatures soar past the boiling point of water. These are the thermophiles and hyperthermophiles, microscopic architects of life that thrive in conditions that would instantly destroy most other organisms. Picture the vibrant, otherworldly colors of Yellowstone's grand prismatic spring, not just a beautiful sight, but a bustling city of these heat-loving microbes. Or plunge deeper into the crushing darkness of the ocean floor, where volcanic vents spew superheated, mineral-rich water. Here, in these deep-sea hydrothermal vents, life flourishes without a single ray of sunlight, drawing energy from chemical reactions, a process called chemosynthesis. These tiny beings are not just surviving, they are dancing in an inferno, showcasing a profound ability to adapt. But life isn't only drawn to the fire. It also embraces the profound chill. High in the polar regions, within ancient glaciers, or in the deep, frigid embrace of the ocean, live the psychrophiles. These cold-loving microbes possess special proteins and membranes that allow them to function perfectly at temperatures where other life forms would simply freeze solid. Think of them as tiny ice carvers, finding warmth and sustenance in what we perceive as an inhospitable, frozen wasteland. Their existence paints a vivid picture of how life might cling to icy moons like Europa or Enceladus, where vast subsurface oceans lie hidden beneath thick crusts of ice. And then there are the pioneers who brave the most corrosive or saltiest frontiers, the acidophiles. Flourish in environments as acidic as battery acid, often found near volcanoes or in industrial runoff, transforming toxic landscapes into living canvases. Conversely, alkaliphiles prefer the sting of highly alkaline conditions. And for those who find solace in salt, there are the halophiles, painting salt flats and hypersaline lakes like the Dead Sea in hues of pink and purple, their cells uniquely designed to prevent desiccation in incredibly briny waters. They teach us that even seemingly barren, mineral-rich landscapes can be teeming with unseen life. Some even endure immense pressure, the piezophiles of the deep ocean, thriving under the weight of miles of water, perfectly at home where pressure would crush a submarine. What makes these tiny beings so extraordinary? Their secret lies in unique biological machinery, specialized enzymes that function at extreme temperatures, robust cell walls, and sophisticated DNA repair mechanisms that mend damage from harsh radiation. They are master chemists, engineers, and survivors, constantly pushing the boundaries of what we consider habitable. Why do these incredible earthlings capture the imagination of astrobiologists? Because they are our most compelling argument that life might exist beyond Earth, thriving in environments that once seemed utterly alien to our concept of habitability. They are living proof that life, once ignited, finds a way, even in conditions that mirror the most desolate places in our solar system. And this brings us to another fascinating aspect of astrobiology: terrestrial analogues. Terrestrial analogues are places on Earth that, in their extreme conditions, remarkably resemble the environments we find on other planets and moons. They are our cosmic laboratories, allowing us to study extremophiles and test our instruments, methods, and theories right here at home, before sending them millions of miles away. They offer a window into what extraterrestrial life might look like, how it might survive, and what biosignatures, evidence of life, we should be searching for. Take, for instance, the Atacama Desert in Chile. It's one of the driest places on Earth, a Martian landscape mirrored. Its hyper-arid soil, intense ultraviolet radiation, and high levels of oxidizing compounds make it an almost perfect stand-in for the surface of Mars. Scientists study microbial communities clinging to life within salt crusts or beneath rocks, learning how life might adapt to the red planet's harsh conditions. They test Mars rovers and drill bits there, preparing them for their deep space voyages, learning to distinguish between geological features and potential signs of ancient or extant Martian life. Travel to the opposite pole, to the Antarctic dry valleys. Here, extreme cold, dryness, and intense winds carve a landscape eerily similar to parts of Mars. The permafrost holds ice-encased microbes, offering clues to how life might persist in Mars's frozen subsurface. Lakes under the ice, like those in Antarctica, are also considered analogues for the potential subglacial oceans of Jupiter's moon Europa or Saturn's moon Enceladus. These isolated liquid water environments, cut off from sunlight, could harbor unique chemosynthetic ecosystems, much like the deep-sea vents here on Earth. Nor consider the Rio Tinto River in Spain, a vivid, blood-red waterway due to its extremely acidic, iron-rich waters, fed by underground mineral deposits. The river is home to a robust community of acidophilic microbes, which thrive on the iron and sulfur present. This unique ecosystem provides a living model for what ancient Mars might have looked like, a planet once flowing with iron-rich acidic waters, potentially teeming with similar microbial life. Another dramatic analog is Dalol in Ethiopia, a landscape of vibrant, acidic, and hypersaline hydrothermal pools so extreme that researchers are finding novel forms of microbial life that redefine our understanding of survival, echoing conditions that could exist on other planetary bodies. These terrestrial analogues are not just exotic tourist destinations for scientists. They are vital training grounds. They help us understand the limits of life, predict where else life might emerge, and design missions that can effectively search for it. They teach us that our definitions of habitable might have been far too narrow, constrained by our own Earth-centric perspective. These tiny, resilient beings on Earth, thriving in what we once called impossible conditions, remind us that the universe may hold secrets of life far stranger and more wonderful than we can yet fully grasp. But if such life exists on distant worlds, how would we recognize it? How would we ever know if life exists elsewhere? How would we recognize its presence across the vast distances of space? The answers, dear listener, might not come as a flashing beacon or a grand proclamation, but as subtle whispers, faint echoes, and delicate fingerprints left behind by life. These are what scientists call biosignatures. Imagine the universe as an ancient, sprawling library filled with countless planets, each a potential story waiting to be told. Most of these stories are unwritten, their pages blank. But if a world has hosted life, even microbial life, it leaves behind unique clues, like a cosmic author signing their work in an invisible ink, waiting for a keen eye to decipher it. This is the art and science of life detection, becoming cosmic detectives, searching for these profound signatures. Plan. These biosignatures come in many forms, each a different kind of clue. Some are like ancient etchings in stone, enduring through eons. These are the morphological biosignatures, the physical imprints of life. Think of a tiny, fossilized microorganism, its delicate shape preserved in rock, a miniature ghost from a time long past. On Earth, we find such microfossils, tiny echoes of our planet's earliest life forms. We also see grander structures like stromatolites, layered, dome-shaped rocks built by colonies of microbes over vast stretches of time, like tiny living architects shaping their environment, leaving behind their layered cities as monumental testaments to their existence. If we were to find similar layered structures on another world, with characteristics that strongly suggest biological construction rather than purely geological forces, it would be a thrilling clue, a whisper from a distant epoch. But life doesn't just leave behind shapes. It also leaves behind a distinct chemical scent, a molecular aroma that can be far more telling. These are the chemical or molecular biosignatures. Life, as we know it, is built from complex organic molecules, the amino acids that form proteins, the lipids that make up cell membranes, the nucleic acids that carry genetic information. Finding these building blocks on another planet would be exciting, but not necessarily definitive. After all, many simple organic molecules can form spontaneously in space and on planets through non-biological processes. It's like finding letters of the alphabet. They're necessary for a story, but they don't prove a story was written. The real puzzle piece, the truly profound clue, often lies in the patterns of these molecules. One such pattern is chirality, often called the handedness of molecules. Imagine your own hands. They are mirror images of each other, but you can't perfectly superimpose one on the other. Molecules can also have a left-handed or right-handed orientation. Terrestrial life, almost without exception, uses only one hand for certain types of molecules. For instance, all amino acids in proteins are left-handed. If we were to find a sample of organic molecules on Mars or Europa that showed a distinct preference for one-handedness over the other, it would be like finding a whole paragraph written in a consistent script, strongly suggesting a biological author. This specific preference is incredibly difficult to achieve through random abiotic chemistry, making it a powerful biosignature. Another subtle chemical signature involves isotopic fractionation. Atoms of the same element can come in slightly different weights, called isotopes. For example, carbon has a common, lighter isotope, carbon-12, and a heavier one, carbon-13. Life, being efficient, often prefers to use the lighter isotopes during metabolic processes because they are easier to move and react. So, if we find a rock or an atmospheric gas on another world that is unusually enriched in lighter isotopes compared to the expected cosmic abundance, it could be a sign that biological processes have been at work, selectively picking and choosing their atomic building blocks. It's a faint yet persistent signature, like a faint hum indicating an engine at work. Then there are the grandest, most visible biosignatures, those etched across an entire world. These are the atmospheric biosignatures, the very breath of a planet. Our own Earth's atmosphere, for example, is far from equilibrium. It's rich in oxygen, a highly reactive gas, and also contains methane, which rapidly breaks down in oxygen's presence. These two gases shouldn't coexist in such quantities for long without a constant source. And that source on Earth is overwhelmingly life. Plants and microbes constantly producing oxygen through photosynthesis, and other microbes releasing methane as a byproduct of their metabolism. This planetary chemical imbalance, this energetic disequilibrium, is a powerful telltale sign that life is actively reshaping its environment. Imagine staring through a powerful telescope at a distant exoplanet, a world light years away. If we could analyze the light filtering through its atmosphere, looking for combinations of gases that strongly suggest biological activity, perhaps abundant oxygen alongside methane, or other intriguing chemical pairings like nitrous oxide, it would be like hearing a chorus of voices from across the cosmos. Telescopes like the James Webb Space Telescope are already beginning this incredible work, sifting through the light of distant suns for these planetary breath prints. But the quest for biosignatures is not without its challenges, much like any great detective story. We must be incredibly careful to avoid false positives, situations where abiotic, non-biological processes mimic the signs of life. For instance, Some geological processes, like serpentinization, can produce methane, confusing our search for biological sources. Conversely, we must also guard against false negatives, missing life that is truly there, perhaps because its signatures are too faint, localized, or have been degraded over time. The universe is vast and creative, and life might express itself in ways we haven't even imagined. This is why context is paramount. A single biosignature, no matter how promising, is rarely enough. We need multiple lines of evidence, layers of clues that reinforce each other, building an undeniable case. We need to understand the geological and environmental history of a world to piece together the full story before making any profound declarations. It's like gathering evidence in a courtroom. One piece might be circumstantial, but a whole tapestry of evidence can lead to an irrefutable conclusion. The search for biosignatures is an ongoing journey, an incredible testament to human curiosity. From scrutinizing ancient rocks with microscopes to sniffing the atmospheres of distant exoplanets with grand telescopes, we are constantly refining our tools and our understanding. Each new discovery, each new technique brings us closer to answering that fundamental question, to perhaps one day finding a definitive signature, a truly undeniable echo of life beyond Earth. As our understanding of these delicate signs deepens, so too does our appreciation for the intricate dance of life on our own blue marble. And with every passing night, our dreams are filled with the possibilities of what wonders the cosmos truly holds, gently preparing us for the next chapter in our astrobiological exploration. The fascinating worlds themselves, where these biosignatures might one day be found. Among the most enchanting and mysterious places in our universe are the water worlds and ocean moons. These are not merely distant points of light, but real celestial bodies, many of them tucked away in the cold, dark corners of space, yet holding the potential for warmth, liquid, and perhaps life. Imagine, if you will, the serene glow of our own moon. But now picture it as a giant, pristine snowball, orbiting the colossal, swirling jewel that is Jupiter. This isn't just any snowball. It's Europa. From a distance, it appears as smooth and unblemished as a pearl, yet closer inspection reveals a mesmerizing tapestry of cracks, ridges, and faint reddish lines. Scars on its icy skin, telling tales of immense forces at play beneath. These aren't just cosmetic imperfections, they are the surface manifestation of a dynamic, churning world. Beneath that shell, scientists strongly believe, lies a vast ocean of liquid water, more water than all of Earth's oceans combined. Think of it, a global ocean, perhaps 60 to 100 miles deep, kept from freezing solid by an incredible cosmic dance. Jupiter's immense gravity, a celestial sculptor, constantly flexes and kneads Europa's interior as it orbits. This constant gravitational tug-of-war generates friction, much like repeatedly bending a paperclip warms it up. This tidal heating is the moon's internal furnace, preventing its deep waters from becoming an utterly frozen wasteland. And in that perpetual twilight zone, far beneath the sun's gentle touch, could life truly exist? The thought is both humbling and exhilarating. We envision potential energy sources, perhaps hydrothermal vents on the ocean floor, similar to those found in Earth's deep seas. Here, ecosystems thrive in perpetual darkness, nourished by chemical energy rather than sunlight. Imagine towering chimneys exhaling superheated mineral-rich plumes, creating oases of chemical abundance. Could these be the nurseries for alien microbes, simple yet resilient, perhaps even more complex forms of life that have adapted to a world without sunlight? Then there's Enceladus, a smaller yet equally captivating moon orbiting Saturn. Unlike Europa, which keeps its secrets tightly sealed beneath miles of ice, Enceladus is a cosmic show-off, generously spraying its very essence into space. From its south pole, colossal geysers erupt, plumes of water, ice, and vapor jetting hundreds of miles above the moon's surface, creating a faint, shimmering halo around it. These plumes, a phenomenon observed directly by the Cassini spacecraft, are like nature's own probe, delivering samples of Enceladus's subsurface ocean directly to us. And what have these precious samples revealed? Not just water, but also salts, organic molecules, the very building blocks of life, and even molecular hydrogen. The presence of hydrogen is particularly exciting, suggesting hydrothermal activity where water reacts with hot rock, a process that could provide chemical energy for life. Enceladus's ocean, though smaller than Europa's, appears to be an active, dynamic environment, warm enough to sustain liquid water with a rocky sea floor, and the ingredients that could spark and sustain a nascent biology. It's a tantalizing prospect, a world actively offering clues to its inner workings, almost inviting us to investigate further. But these two aren't alone. Our solar system is a veritable treasure trove of ocean moons. Ganymede, Jupiter's largest moon, and Callisto, another Jovian satellite, are also thought to harbor vast subsurface oceans. Even distant Pluto, a dwarf planet once considered a cold, barren rock, now shows evidence of a deep, ancient subsurface ocean beneath its heart-shaped plain, Sputnik Planitia. And Ceres, a dwarf planet in the asteroid belt, displays cryovolcanoes, suggesting a subsurface reservoir of briny water that occasionally breaks through to the surface. The common thread through all these wondrous places is liquid water. It's considered the universal solvent, a medium in which complex chemical reactions can occur, allowing the intricate dance of life to begin and evolve. For surface-dwelling life, stellar heating, like from our sun, is crucial. But for these hidden oceans, the tidal heating from their gas giant parents provides that essential warmth, proving that life's potential isn't limited to the sunlit surface of planets. And what about beyond our solar system? The exploration of exoplanets has opened up an even vaster canvas of possibilities. Imagine a world, not just with oceans, but entirely an ocean. A water world exoplanet, covered perhaps hundreds of miles deep in liquid. Astronomers have identified candidates that fit this description, massive super-Earths, whose densities suggest a significant water content, potentially making them deep-sea environments on a planetary scale. These worlds, too, might orbit within their stars' habitable zones, the precise orbital distance where temperatures are just right for liquid water to exist on the surface, neither too hot to boil away, nor too cold to freeze solid. Detecting these deep exoplanet oceans is a monumental task, relying on subtle clues from telescopic observations such as a planet's density or atmospheric composition. Yet the sheer number of exoplanets discovered fuels our imagination, suggesting that ocean worlds might be a common feature across the galaxy, each a unique cosmic aquarium waiting for discovery. The implications of these water worlds and ocean moons are profound for astrobiology. They tell us that the conditions for life, or at least for its fundamental building blocks and a suitable environment, might be far more common than once thought. We're not just looking for Earth-like planets, but for any place where liquid water, an energy source, and the necessary chemical ingredients can coexist for a sustained period. Each shimmer, each ripple of liquid water, whether on a distant exoplanet or beneath the frozen crust of a moon in our own cosmic backyard, sings a silent promise of potential. The implications of these water worlds and ocean moons are profound for astrobiology. They tell us that the conditions for life might be far more common than once thought. Each shimmer, each ripple of liquid water sings a silent promise of potential. Yet as we search for microbial life in these hidden oceans, another question beckons from the darkness beyond. While we search for simple life in our solar system's hidden oceans, another profound question stirs in our hearts. What if intelligence has already arisen elsewhere? What if, among those countless stars, other minds are looking back? It's a whisper that has echoed through human minds for millennia, a curiosity as old as gazing up at the scattered starlight. This deep yearning to know if there are other thinking minds out there, perhaps gazing back at their own starlit heavens, led to the birth of a fascinating scientific endeavor known as SETI, the search for extraterrestrial intelligence. Imagine, if you will, the universe as an immense, silent forest at night. Our planet Earth is but one small campfire flickering warmly, and SETI is like quietly listening into that vast darkness, not for the rustle of leaves or the chirping of crickets, but for another distant campfire song, a melody of intelligent design carried on the cosmic winds. For most of human history, this search was confined to philosophy and dreams. But with the advent of powerful technologies, particularly in the 20th century, we gained the tools to actually listen. Our primary ears in this grand cosmic concert are immense radio telescopes. Picture these majestic structures like colossal listening dishes, turning their silent faces towards the heavens. They are designed to capture faint radio waves, the very same kind of electromagnetic radiation that brings music to your car radio or pictures to your television, but coming from unimaginably distant stars. Why radio waves? Well, radio waves are like the universe's preferred medium for long-distance communication. They travel at the speed of light, unimpeded by cosmic dust or gas, and can cross vast interstellar distances without losing too much energy. They are also relatively easy to generate and detect with technology we understand. It's a logical assumption that another advanced civilization, wanting to signal its presence, might choose this robust and far-reaching method. One of the most promising channels we listen to is a specific band of frequencies often called the water hole. This celestial watering hole, if you will, is a quiet cosmic meeting ground. It's nestled between the radio emission frequencies of hydrogen, the most abundant element in the universe, which quietly hums at 1420 megahertz, also known as the 21-centimeter line, and the hydroxyl radical, which emits at frequencies around 1612 megahertz. Together, hydrogen, H, and hydroxyl, OH, form water, H2O, the very essence of life as we know it. Scientists theorize that an intelligent civilization might choose this specific frequency range because it's a relatively quiet part of the radio spectrum, less cluttered by natural cosmic noise and universally recognizable. It's like agreeing to meet at a famous landmark in a bustling city. Everyone knows where to look. The challenge, though, is immense. It's often compared to searching for a needle in a haystack. But a haystack the size of the Milky Way galaxy, filled with billions of stars, and each star potentially surrounded by its own planetary system. And we don't even know what that needle, the signal, might sound like, or where it might originate from. It could be a continuous beacon, a series of pulses, or a complex message embedded with mathematical constants like the value of pi, or a sequence of prime numbers, a universal language that any intelligent mind could potentially decode. This quest isn't just about listening, though. It's also about understanding the probabilities. Decades ago, a brilliant astrophysicist named Frank Drake, one of the pioneers of SETI, conceived of an equation that bears his name, the Drake equation. It's not a formula to give us an exact number, but rather a profound thought experiment, a way to organize our ignorance and consider all the factors that would need to align for us to find intelligent life. Imagine building a gentle cascade of conditions. First, how many stars form each year in our galaxy? Then, how many of those stars have planets? And how many of those planets could potentially support life? From there, how many of those life-supporting planets actually develop life? And then, how many of those develop intelligent life? And finally, how many of those intelligent civilizations develop technology that releases detectable signs into space? And for how long do they remain detectable? Each step in this cascade introduces a huge uncertainty. We've made incredible strides in understanding the first few factors, thanks to discoveries of exoplanets. We now know that planets are incredibly common, orbiting most stars. But the subsequent factors, like the probability of life arising or intelligence evolving, or how long a civilization might last, are still deep mysteries, making the final number anywhere from us to millions. This brings us to another fascinating puzzle, often whispered about with a touch of cosmic awe, the Fermi paradox. Named after the brilliant physicist Enrico Fermi, it's a simple yet profound question. If the universe is so vast, and there are so many stars, and potentially so many chances for life to arise, then where is everybody? Why haven't we heard anything? Why isn't the sky filled with the chatter of countless civilizations? The silence is truly deafening, isn't it? There are many possible answers, each one a story in itself. Perhaps intelligent life is incredibly rare, a precious cosmic accident. Perhaps civilizations don't last very long, succumbing to self-destruction or natural catastrophes. Maybe they exist, but they are too far away, their signals too weak to reach us across the light years. Or perhaps, and this is a more intriguing thought, they are simply different. They might communicate in ways we haven't even conceived of. Or they might choose to remain silent, observing us from a distance, like gentle astronomers watching a new star flicker into existence. T isn't just about listening for radio waves anymore either. There's also optical SETI, a more recent branch of the search. Instead of radio dishes, imagine giant telescopes, not looking for images, but for fleeting, intense flashes of light, pulsed lasers. A highly advanced civilization might use powerful lasers to send brief, directed messages across vast distances. These pulses could be incredibly powerful, designed to stand out against the natural glimmer of stars. It's like looking for a tiny, deliberate blink in the vast, winking eye of the night sky. The beauty of SETI lies in its patience, its optimism, and its embrace of the unknown. It's a multi-generational quest, a cosmic act of hopeful listening. Every day, arrays of radio telescopes, like the Allen Telescope Array in California or the colossal Green Bank Telescope in West Virginia, gently sweep across the sky, processing unimaginable amounts of data. They're not just listening for a simple beep, they're looking for patterns, for anomalies, for anything that suggests intent, a plush techno-signature, a sign of technology rather than just natural cosmic phenomena. It's a testament to our profound curiosity, a quiet declaration that we are ready to reach out, to extend our ears and our minds beyond our earthly home. Even without a definitive signal, the search itself enriches us, reminding us of our place in the cosmos, fostering a sense of shared destiny with whatever life might emerge among the stars. It teaches us humility, persistence, and the boundless potential of the universe. And so, as we consider this cosmic vigil, this silent act of listening across the light years, we can dream of the day when that whisper might turn into a clear voice, or a distant flash might reveal a hidden message. The search continues, ever present, ever hopeful, as gentle as the pull of gravity, and as constant as the turning of the constellations. Tomorrow, we will gently turn our gaze from the distant whispers of potential intelligence to a different kind of cosmic communication, one that is truly, deeply personal. The story of how the very elements that make up our bodies were forged in the hearts of dying stars. For now, let the quietude of the search lull you into a peaceful slumber, knowing that the universe holds infinite possibilities, waiting to be discovered, one gentle listen at a time. Our thoughts turn now from the possibility of finding life to the profound responsibility that comes with seeking it. Tonight, we'll gently explore a concept known as planetary protection, and then, with a soft sigh, contemplate the delicate ethics surrounding the very idea of contact with intelligent life from other stars. Picture, if you will, the universe as an immense, ancient garden, teeming with countless tiny, secret pockets of potential. Some are vibrant with life, others lie dormant, waiting for just the right conditions to awaken. When we send our robotic emissaries, our intrepid spacecraft, out into this cosmic garden, we become, in a sense, cosmic gardeners ourselves. And like any good gardener, we must be careful not to introduce invasive species that could harm the native flora, or inadvertently disrupt the delicate balance of an ecosystem we barely understand. This is the heart of planetary protection. It's a guiding principle, a quiet promise we make to the cosmos to prevent biological contamination. This promise has two gentle facets. First, there's forward contamination. This is the effort to ensure that our spacecraft, which are built here on Earth, don't carry earthbound microbes, tiny bacteria, fungi, or spores to other celestial bodies. Imagine sending a pristine scientific instrument to Mars, hoping to find signs of ancient Martian life, only to discover later that the life you detected was merely a hardy hitchhiker from our own planet, a microscopic stowaway that survived the journey. That wouldn't just be a scientific disappointment, it would be a profound cosmic misunderstanding, a blurring of the lines between alien and terrestrial. It's like a detective meticulously sifting through a crime scene, making absolutely certain that no evidence is accidentally introduced that could mislead the investigation. To prevent this, our spacecraft undergo incredibly stringent sterilization protocols. They are assembled in super clean rooms, where the air is filtered to remove even the tiniest dust particles. Components are baked at high temperatures, blasted with ultraviolet light, or bathed in special chemical solutions to reduce the bioburden, the count of living microbes, to an absolute minimum. It's a meticulous, almost ritualistic cleansing, performed with the utmost respect for the unknown. Organizations like COSPAR, the Committee on Space Research, have developed a classification system, categories from I to V, that dictate how clean a mission needs to be based on its destination and objectives. For instance, a mission destined for a potentially habitable body, like Mars or Jupiter's moon Europa, places where liquid water might exist and thus where life might conceivably thrive, falls under Category 4. These missions demand the highest level of sterilization, a cosmic hygiene that reflects our deepest scientific integrity. Then there's the flip side of the coin. Then there's backward contamination. This is the equally vital effort to ensure that any samples we might eventually bring back to Earth from another celestial body do not carry extraterrestrial microbes that could pose a threat to our own biosphere. While the scientific consensus is that the chances of alien microbes being harmful to Earth life are exceedingly low, especially from planets or moons that are vastly different from our own, the precaution is paramount. It's an act of profound humility and foresight. Imagine, for a moment, the care we take when a rare, exotic plant or animal is introduced to a new environment on Earth. We have strict quarantines, careful monitoring. In space, these measures become infinitely more critical. Any future sample return mission from Mars, for example, would involve containment facilities of an unprecedented level of security, designed to isolate and meticulously analyze any returned material before it ever touches Earth's open air. It's a cosmic quarantine, a gentle, protective embrace around our home planet. So, planetary protection is about preserving the scientific integrity of our quest for life, ensuring that when we find it, we know it's truly alien. It's about protecting nascent life elsewhere from our accidental touch, and protecting our own precious Earth from the truly unknown. It's a testament to our growing wisdom as we venture forth into the universe. But what about the truly grand contemplation? What if, beyond microbes, we were to encounter intelligence? This brings us to the profound and ethically complex topic of the ethics of contact. For decades, we've been listening. The SETI project, the search for extraterrestrial intelligence, has been patiently sweeping the skies with radio telescopes like a solitary sentinel listening for a distant whisper in the vast cosmic silence. This passive listening, this quiet hope, carries little ethical dilemma. We are merely observing, not interfering. But what if we were to actively reach out? What if we were to send our own messages, purposefully, into the cosmic ocean? This is known as METI, Messaging Extraterrestrial Intelligence, and it's a topic that stirs deeply philosophical debates. Imagine the decision to shout into the void or to remain a silent observer. The arguments against actively messaging are compelling and often voiced with a sense of cautious humility. We simply don't know what kind of intelligence might be out there. Their intentions could be benevolent, indifferent, or even frighteningly malevolent. They might be thousands, millions, or even billions of years more advanced than us, possessing technologies and understandings that are utterly beyond our comprehension. To attract their attention could be akin to an ant colony deliberately signaling its presence to a species far greater than itself. There's a chilling concept known as the dark forest theory, which suggests that civilizations in the universe might choose to remain silent, hiding their existence precisely because any signal could reveal their location to potentially hostile or exploitative others. It's a cosmic game of hide and seek, where the stakes are existential. Furthermore, there's the question of consensus. Does humanity, as a whole, have the right to speak for all of Earth, to reveal our presence without a truly global, democratic deliberation? What impact would such contact, even a one-way message, have on our diverse cultures, religions, and societies? It could be a shockwave rippling through every aspect of human existence. Yet, there are also gentle voices arguing for METI. They speak of the potential for shared knowledge, for an expansion of understanding that could lift humanity to new heights. They suggest that perhaps any civilization advanced enough to travel across vast interstellar distances or to detect our signals would also be wise enough or benevolent enough to engage in peaceful exchange. They might already know we're here, having detected the faint echoes of our radio and TV broadcasts that have been leaking into space for a century. To not engage, some argue, would be to squander an opportunity for cosmic connection, for finding our place in a larger tapestry of life. Of course, the sheer distances involved mean that any conversation would be incredibly slow. A message sent to a star system just 100 light-years away would take a century to arrive, and another century for a reply to return. This isn't a dialogue. It's more like sending a message in a bottle across an unfathomably vast ocean, hoping someone finds it, understands it, and perhaps, someday, sends one back. The nature of communication across light years transforms conversation into a patient exchange of cosmic artifacts. There are no universally agreed upon international laws or protocols for how to handle first contact, whether it's the discovery of microbial life or the reception of an intelligent signal. We stand at the precipice of a profound unknown, guided only by our scientific curiosity, our ethical considerations, and our hopes and fears. It's a contemplation of our place in the universe, a silent question we ask ourselves. How do we act as responsible inhabitants of this pale blue dot as we begin to peer into the boundless ocean of stars? And as we consider these deep questions of our cosmic responsibilities, our minds naturally drift to the tools and methods we use to explore these distant worlds, leading us gently into our next thoughtful exploration. The incredible engineering marvels that make space exploration possible. Close your eyes now and imagine those silent, lonely vessels carrying our hopes and our cautions across the vast, waiting darkness. Let us consider something truly profound, a whisper that echoes through the very fabric of the universe, the universal principles of evolution. It's a melody of change, a dance of adaptation, played out not just on our pale blue dot, but potentially across countless worlds bathed in the light of distant suns. Imagine, for a moment, life taking root on a planet utterly unlike Earth. Perhaps a world shrouded in eternal twilight, warmed by the faint glow of a red dwarf star, where the very air shimmers with exotic chemistry. Or a planet orbiting a gas giant, perpetually illuminated by aurora, its oceans a rich, viscous broth of unfamiliar molecules. No matter how alien the environment, scientists ponder that the core principles guiding life's journey would likely remain remarkably similar, sculpted by the same immutable laws of physics and chemistry that govern our own existence. The first most fundamental principle is variation. Think of it as the universe's endless creativity, the subtle differences that emerge even in seemingly identical beginnings. On Earth, we see it in the unique patterns of a snowflake or the diverse shades of a forest leaf. In the realm of life, this means no two organisms are ever truly identical. There are tiny, inheritable differences in their form, their function, their very molecular machinery. These variations are the raw material, the spectrum of possibilities upon which evolution acts. On an alien world, perhaps the variations lie in how efficiently an organism can absorb exotic radiation, or how its cells process a unique array of atmospheric gases, or even the subtle nuances in its bioluminescent patterns. Without these small, inheritable differences, life would remain static, unable to adapt to the ever-changing whispers of its environment. Hand in hand with variation comes heredity. For evolution to proceed, these variations must be passed down from one generation to the next. It's the universe's way of remembering, a cosmic thread weaving through time. On Earth, this thread is primarily DNA, a magnificent double helix encoding the blueprints of life. But on another world, the carrier of heredity might be utterly different, perhaps a crystalline structure, or a complex array of self-replicating proteins, or something we cannot even conceive. What matters is the ability to transmit traits, ensuring that a beneficial adaptation in a parent can be shared with its offspring, allowing that advantageous trait to persist and spread through a population. Without heredity, each generation would start anew, and evolution, that slow, deliberate sculptor, would have no clay to mold. Now let us introduce the master sculptor itself, natural selection. This is not a conscious force, but rather the elegant, relentless consequence of variation and heredity interacting with the environment. Imagine our alien twilight world. Some organisms might by chance possess a variation that allows them to absorb a wider spectrum of the red dwarf's dim light, making them better at photosynthesis. Others might have a slightly more robust outer layer, protecting them from a particular form of atmospheric radiation. The environment, in its silent, impartial way, favors those best suited to its conditions. These fortunate individuals are more likely to survive, to thrive, and crucially, to reproduce, passing on their advantageous traits. Those less suited, though no less beautiful or complex, might struggle, leave fewer offspring, or eventually fade. Over countless generations, this gentle filtering process shapes populations, guiding them towards a finer harmony with their surroundings. It's a continuous conversation between life and its home, where the environment poses challenges and life responds with ingenious solutions. The beautiful outcome of natural selection acting over vast spans of time is adaptation. Organisms become exquisitely attuned to their specific ecological niche, like a perfectly fitted key in a cosmic lock. An adaptation might be a specialized enzyme to digest an unusual alien mineral, or an intricate sensory organ to navigate a dense, foggy atmosphere, or a complex social behavior to survive extreme temperature fluctuations. Each adaptation is a testament to the long history of a species interacting with its unique world. If we were ever to encounter alien life, every aspect of its physiology and behavior would likely be a living archive of its planet's environmental pressures, a silent story of countless adaptations forged over eons. As populations expand and encounter diverse conditions, a fascinating process called divergence unfolds. Imagine a species of alien flora spreading across a continent, some moving into arid plains, others into humid valleys, and still others into cold, mountainous regions. Each subgroup faces different environmental pressures. Over time, natural selection will favor different variations in each area, leading the populations to slowly drift apart, becoming less and less alike. Eventually, they may become so distinct that they can no longer interbreed, forming entirely new species. This is how the rich tapestry of life on Earth and presumably elsewhere is woven, a single ancestral thread branching into an intricate cosmic bush, each twig a unique form of life, perfectly suited to its own corner of the cosmos. And perhaps one of the most compelling universal principles, offering a tantalizing glimpse into what alien life might look like, is convergent evolution. This is the phenomenon where similar environmental pressures independently lead to similar solutions in unrelated lineages. On Earth, we see it in the streamlined bodies of sharks, dolphins, and ancient ichthyosaurs, all adapted for efficient movement through water, or in the independently evolved eyes of insects, octopuses, and vertebrates. If the laws of physics and chemistry truly are universal, then certain optimal solutions to common problems might arise repeatedly across the universe. If an alien world has liquid oceans, might we find streamlined swimmers there too? If it has an atmosphere and requires flight, might there be creatures with wing-like structures, even if their biochemistry is entirely alien? This suggests that while alien life will undoubtedly be astonishingly diverse, there might be recognizable forms or functional equivalents that speak to universal engineering challenges and their elegant, evolutionary solutions. Another intriguing facet is exaptation. where a feature that evolved for one purpose is co-opted for an entirely new one. Think of how feathers, initially evolved for insulation in dinosaurs, later proved incredibly useful for flight. On an alien world, a sensory organ that initially detected atmospheric tremors might, over time, be repurposed for complex communication, leading to advanced social structures. Evolution is a tinkerer, not a grand designer, constantly reusing and repurposing existing structures in novel ways, always finding new paths forward. And finally, while evolution doesn't inherently strive for increasing complexity, the potential for it certainly exists, given stable environments and sufficient energy. From the simplest self-replicators, over eons, evolution can construct organisms of breathtaking intricacy, perhaps even leading to consciousness and intelligence on other worlds. The journey from a single self-replicating molecule to a sentient being capable of gazing at the stars is a long and arduous one, but it is a journey made possible by these universal evolutionary principles. These principles, variation, heredity, natural selection, adaptation, divergence, common descent on a planetary scale, and convergent evolution, are not mere earthly curiosities. They are the fundamental algorithms of life, the cosmic software that likely runs on any planet where the spark of life has taken hold. Understanding them helps us not only appreciate the incredible diversity of life here at home, but also opens our minds to the unimaginable forms and fascinating pathways that life might have taken or be taking in the distant, starlit reaches of the cosmos. As we ponder these universal rules, our minds naturally turn to the immense and humbling question of how we might ever detect such wondrous, diverse life, and what incredible messages it might hold for us across the light years. The story doesn't end with what we know today. The future unfolds like a grand cosmic ballet, choreographed by human curiosity and scientific endeavor. Our next steps into the astrobiological unknown are not just whispers in the dark, but carefully planned expeditions, each designed to peel back another layer of the universe's most profound mysteries. We are preparing to send out even more intrepid messengers, tiny robotic ambassadors, to places we've only just begun to understand. One of the most ambitious chapters awaiting us centers on Mars, our rusty neighbor. The Perseverance rover, currently diligently exploring Jezero crater, is not just observing, it's also a celestial librarian, carefully collecting and caching samples of Martian rock and regolith. Picture these samples as ancient letters, sealed for billions of years, holding the potential secrets of Mars's watery past, and perhaps even fossilized remnants of ancient life. The next vital piece of this puzzle is the Mars Sample Return mission. This monumental undertaking envisions a future lander dispatching a small rocket from the Martian surface, carrying these precious vials, these cosmic time capsules, back to Earth. Once here, in pristine laboratories, scientists with tools far more powerful than any rover could carry will meticulously analyze them, searching for definitive biosignatures, chemical fingerprints, or microscopic structures that would serve as undeniable proof that life once stirred on Mars. This isn't just about finding microscopic bugs, it's about understanding if life could originate independently on another world, a question that redefines our understanding of biology itself. But our gaze extends far beyond Mars, into the frigid, icy embrace of the outer solar system. Here, tucked away in the shadows of gas giants, lie worlds that astronomers once dismissed as barren, but now recognize as some of the most promising havens for life beyond Earth. Jupiter's moon, Europa, a pristine white marble crisscrossed with icy fractures, is a prime target. Beneath its miles-thick frozen shell, scientists believe, lies a vast, salty ocean, warmed by tidal forces from Jupiter, potentially teeming with hydrothermal vents, echoes of the life-giving environments found deep within Earth's own oceans. The Europa Clipper mission, set to launch soon, will be like a tireless hummingbird, performing dozens of close flybys of Europa. It won't land, but it will carry a sophisticated suite of instruments, radar, to penetrate the ice and map the ocean's depth, thermal imagers to spot warm spots or plumes, and magnetometers to confirm the ocean's presence and composition. It will act as a scout, seeking out the most promising locations where the ocean might be accessible, or where plumes of water might be erupting into space, offering tantalizing samples without ever having to drill. If we are lucky, it might even detect organic molecules within these plumes, the very building blocks of life. Following the Clipper's pioneering reconnaissance, a truly audacious concept, the Europa lander might one day gently kiss Europa's frozen crust. Imagine a robotic explorer equipped with a drill capable of penetrating through several meters of ice, designed to reach that hidden ocean. Once there, a suite of miniature sensors and microscopes would plunge into the alien waters, searching in situ for signs of microbial life. This would be an unprecedented feat of engineering and exploration, a direct encounter with an extraterrestrial ocean, pushing the boundaries of what we thought possible. Further out still, where Saturn casts its magnificent rings, another incredible journey awaits on Titan, its largest moon. Titan is unique in our solar system, shrouded in a thick, nitrogen-rich atmosphere, where methane and ethane replace water, forming lakes, rivers, and even rain. Here, the Dragonfly mission, a groundbreaking rotorcraft drone, will embark on a multi-year adventure. Picture a giant robotic bumblebee designed to fly from location to location, exploring Titan's diverse landscapes, its equatorial dunes, the shorelines of its hydrocarbon lakes, and potential cryovolcanic flows. Dragonfly carries instruments to analyze the complex organic chemistry happening on Titan, searching for the precursors to life, or perhaps even a form of life that utilizes hydrocarbons instead of water as its solvent. It's a mission designed to explore an entirely different astrobiological pathway, a world where the familiar rules of Earth-based life might not apply. And not to be outdone, Saturn's moon Enceladus, with its famous geysers continuously spewing icy plumes into space, also holds immense promise. Concepts like the Enceladus Orbilander envision a spacecraft that could both orbit the moon to study its plumes remotely and then land near the South Polar region to collect samples directly from the surface, where fresh ocean material is constantly being deposited. This direct sampling, much like catching snowflakes, would allow scientists to search for specific biosignatures, including amino acids or even microbial cells carried aloft from the ocean below. Our future astrobiological quest isn't confined to our solar system. The quest for life also turns our gaze outward towards the thousands of exoplanets we've discovered orbiting distant stars. Current and future space telescopes are our eyes to these far-flung worlds. The James Webb Space Telescope, JWST, already dazzling us with its cosmic vistas, is proving invaluable in characterizing the atmospheres of exoplanets, searching for telltale chemical signatures like water vapor, carbon dioxide, and methane. Looking further ahead, conceptual missions like LUVOIR, Large UV Optical IR Surveyor, or HABEX, Habitable Exoplanet Observatory, represent our dreams of building truly colossal space telescopes. These would be cosmic eyes, equipped with advanced coronagraphs, star shades that would block out the blinding glare of a parent star, allowing us to directly image Earth-sized planets and analyze their atmospheres in exquisite detail. Imagine seeing the light from an exoplanet split into a rainbow of colors, revealing the presence of oxygen, methane, or even seasonal changes that hint at global biology. These powerful instruments could detect biosignatures from light years away, turning dots of light into potential havens for alien life. Beyond these magnificent missions, a tapestry of technological advancements underpins all future astrobiological endeavors. Artificial intelligence and machine learning are becoming indispensable, sifting through the immense volumes of data gathered by telescopes and rovers, identifying patterns and anomalies that human eyes might miss. Advanced propulsion systems moving beyond traditional chemical rockets are being developed to reduce travel times to the outer solar system and even beyond, making missions to distant ice moons or Kuiper Belt objects more feasible. Miniaturization allows us to pack more scientific punch into smaller, lighter probes. Robotics are becoming more autonomous, capable of making decisions in hazardous environments without constant human intervention, a necessity for missions where light speed delays make real-time control impossible. These endeavors are not just about finding life. They are about understanding ourselves, our place in the vast, silent symphony of the cosmos. Our future in astrobiology is a journey of relentless curiosity, a testament to the human spirit, U0027's desire to unravel the deepest secrets of existence. But what would it truly mean for humanity if one of these missions were to finally send back the unmistakable signal, life found? Imagine a new, unprecedented light dawning upon humanity. Not a physical light in the sky, but a revelation, a truth whispered across the vast cosmic ocean. What if we discovered we are not alone? The journey to that moment would likely be slow, a building crescendo of evidence. It might begin with a subtle anomaly, detected by an instrument like the James Webb Space Telescope, a curious chemical imbalance in the atmosphere of a distant exoplanet, a biosignature hinting at life's processes, perhaps an unexpected abundance of oxygen or methane not easily explained by geology alone, or perhaps a technosignature, a rhythmic pulse of radio waves, too orderly to be natural, picked up by an array of dishes like those at the SETI Institute, a deliberate beacon shining through the cosmic night. The first societal impact wouldn't be mass hysteria, but a profound hush, a global intake of breath as scientists meticulously, repeatedly verify the data, ruling out every earthly explanation. Then, the news would break, not with a bang, but with a quiet, undeniable tremor that shakes the very foundations of human thought. For millennia, humanity has grappled with the question of its uniqueness. Religions, philosophies, and cultures have often placed humanity at the center of creation, a special species on a special planet. The discovery of even microbial life elsewhere, let alone intelligent beings, would be like turning a cosmic mirror towards ourselves. It would force a profound reevaluation of our place in the universe. Is there a divine plan for life beyond Earth? Are we just one of many evolutionary paths? This isn't just a scientific revelation. It's an existential earthquake. The Copernican principle, which taught us that Earth is not the center of the solar system, would expand dramatically. We are not the sole inhabitants of the cosmos. This single fact could redefine our species' identity more than any event in recorded history. This shift would ripple deeply into our diverse belief systems. Some faiths might find their tenets reinforced, seeing the vastness of creation simply expanded, a testament to a greater divine power. Others might face profound challenges, requiring reinterpretations of sacred texts and doctrines. Think of the historical upheavals caused by Galileo's observations, or Darwin's theory of evolution. The discovery of alien life could be an intellectual and spiritual challenge of an even greater magnitude. It would spark global dialogues, a grand tapestry of theological and philosophical discussions unfolding across every continent as humanity collectively grapples with what it means to be human in a universe teeming with life. Beyond the philosophical, the societal impact would ignite an unprecedented scientific and technological boom. Fields like astrobiology, already vibrant, would explode with funding and talent. The search for more life, for different forms of life, would become humanity's paramount quest. New instruments, new methods of analysis, perhaps even entirely new branches of physics and biology would emerge. Imagine the collaborative spirit, nations pooling resources, sharing data, driven by a common profound goal. The discovery of a techno-signature would particularly galvanize efforts towards communication. How do we respond? What language do we use? This isn't just about sending a message, it's about creating a universal dictionary, a cosmic Rosetta Stone. Research into SETI, Search for Extraterrestrial Intelligence, would shift from a niche scientific pursuit to a central pillar of global scientific endeavor, pushing the boundaries of radio astronomy, signal processing, and even artificial intelligence. Such a monumental discovery would inevitably trigger significant political and economic shifts. Would it unite humanity under a common cosmic banner, fostering global cooperation previously thought impossible? Or would it exacerbate existing divisions, with nations vying for first contact or exclusive access to alien knowledge or technology? International bodies, like the United Nations Office for Outer Space Affairs, UN-USA, already dealing with space law and the peaceful uses of outer space, would see their role dramatically expand. New treaties, new protocols for interstellar communication, even new forms of governance might be debated. The economic impact could be immense, redirecting investment into space infrastructure, research, and security. Consider the overview effect that astronauts describe. Seeing Earth from space instills a profound sense of unity and fragility. The discovery of alien life might induce a similar cosmic overview effect, fostering a global consciousness that transcends national borders, reminding us of our shared humanity on this small blue marble. Culturally, the impact would be a fertile ground for an extraordinary renaissance. Artists, writers, musicians, filmmakers, all would find an inexhaustible source of inspiration. Our stories would change, our myths would evolve, reflecting a universe suddenly expanded and populated. How would alien life be portrayed, not just as monsters or saviors, but as complex beings, sparking new forms of art that explore empathy, difference, and the universal experience of existence? Our collective imagination, long captivated by fictional aliens, would now have a tangible anchor, shifting from pure fantasy to speculative realism, enriching our human narrative in countless ways. This societal impact is not merely intellectual, it penetrates the very heart of human creativity. But with profound discovery comes profound responsibility. What are our ethical obligations to alien life, especially if it's microbial and vulnerable or intelligent and vastly different? The concept of planetary protection, already in place to prevent earthly contamination of other worlds and vice versa, governed by organizations like COSPAR, would take on a monumental new significance. If we found life on Mars, for example, even simple bacteria, our approach to future missions would be radically altered to ensure its preservation. When it comes to intelligent life, the ethical questions multiply. How do we initiate contact without imposing our own cultural biases? Should we even contact them? Who speaks for Earth? These aren't easy questions, and the debates would be robust, reflecting the diverse values of our global society. In the grand cosmic scheme, such a discovery might ultimately serve as a catalyst for human unity. Faced with the vastness of the universe and the undeniable presence of other intelligences, our petty differences might diminish in significance. We might finally truly embrace our shared identity as inhabitants of Earth, a small, vibrant oasis in a silent, star-strewn desert. The challenge of understanding and interacting with alien life could become the crucible in which a truly global civilization is forged, united not by fear, but by a shared sense of wonder and curiosity. It would be a recognition that our individual stories, our national histories, are but tiny threads in an infinitely larger, richer tapestry of cosmic existence. And so, as we drift through the silent cosmic ocean of our thoughts tonight, considering these profound societal ripples, we can appreciate the immense significance of our ongoing journey of exploration. The quest for life beyond Earth is not just about finding answers out there. It is, in many ways, about understanding ourselves better, right here. As the stars twinkle quietly above, inviting us deeper into the mysteries of space, perhaps we can now turn our gaze towards the very tools and methods we employ in this incredible search and consider how we actually listen for those distant whispers. Now, as we drift deeper into the quiet stillness of the night, let us turn our gaze from our comfortable cosmic home, our familiar solar system, and cast our thoughts to something even grander, even more profoundly distant, the vast, star-dappled ocean that lies beyond. We've spoken of life within our own sun's embrace, but what of the universe's wider shores? This is the realm of interstellar exploration, a journey not just across space, but across imagination itself. Imagine standing on a silent beach, looking out at an endless sea, knowing there are distant islands, unseen continents, waiting to be discovered. That's a little like how we stand at the edge of our solar system, gazing at the myriad stars, each a distant sun, many perhaps orbited by their own families of planets. The very idea of reaching them feels like a whisper in a dream, a quest for a far-off treasure. Our first tiny footsteps into this immense ocean have already been taken, far, far beyond the orbits of even the most distant planets like Neptune. Two remarkable messengers from humanity are still sailing. These are the Voyager 1 and Voyager 2 probes. Launched in the 1970s, they were designed to explore the outer giants of our solar system. But they kept going, carrying with them a golden record, a kind of cosmic message in a bottle. This record contains sounds and images from Earth, a silent greeting from our world, a snapshot of our existence, should it ever be intercepted by another intelligence in the distant future. In 2012, Voyager 1 achieved a monumental feat. It officially crossed the heliopause, the boundary where the sun's protective bubble of solar wind gives way to the colder, denser, true interstellar medium. Voyager 2 followed suit in 2018. They are now, in essence, truly in interstellar space, the furthest human-made objects ever to venture into the galactic night. But despite their incredible journey, traveling at speeds of over 38,000 miles per hour, they are still moving at a snail's pace compared to the staggering distances involved. To reach our nearest star system, Alpha Centauri, which is a mere 4.37 light-years away, Voyager 1 would still take tens of thousands of years. A light-year, as you know, is the distance light travels in one Earth year, approximately 6 trillion miles. It's a measure that truly humbles us, reminding us of the cosmic scale. So, if our current technology makes even the closest star an odyssey spanning millennia, how might we ever truly explore beyond? This is where the brilliant minds of scientists and engineers begin to dream, pushing the boundaries of what seems possible. One fascinating concept is Project Breakthrough Starshot, a proposed mission that envisions tiny, centimeter-sized spacecraft called nanocraft, propelled to extraordinary speeds by powerful lasers. Imagine a fleet of these small probes, each weighing no more than a few grams, unfurling ultra-thin, highly reflective light sails like gossamer wings catching the sunlight, but instead catching the concentrated beam of lasers from Earth. These laser photons, tiny packets of light, would impart an immense push, accelerating the nanocraft to perhaps 20% of the speed of light. At such incredible velocities, a journey to Alpha Centauri could be reduced to mere decades, perhaps 20 years, a time frame that suddenly feels within reach, at least for sending robotic emissaries. Another more distant, theoretical concepts include fusion rockets, harnessing the power of the stars themselves, or even antimatter propulsion, a futuristic fuel that promises the most efficient energy release known to physics. And of course, the grand, almost mythical idea of a warp drive, bending space-time itself to shorten the journey, a concept still firmly in the realm of science fiction, but one that continues to spark our imagination. Why do we even contemplate such ambitious, technologically demanding journeys? The answer lies at the very heart of astrobiology, the profound question, are we alone? We've discovered thousands of exoplanets, worlds orbiting other stars, many of them potentially rocky and residing in their star's habitable zone, that sweet spot where temperatures might allow for liquid water. To send a probe to such a world, even to just glimpse it up close, would be to begin to answer that question. We could search for direct evidence of life, or at least for the telltale biosignatures in their atmospheres or on their surfaces that hint at its presence. Imagine a probe arriving at a distant exoplanet, a world perhaps very different from our own. What kind of life might it find? Could there be extremophiles thriving in conditions we deem hostile? Or might it find a lush, vibrant biosphere teeming with organisms unlike anything we've ever conceived? Perhaps it would reveal that life is incredibly rare, a precious cosmic anomaly. Or conversely, it might show us that life is common, a resilient phenomenon that takes root wherever conditions allow. Even if direct exploration remains a distant dream for physical humans, the data these probes could send back would be invaluable. It would not only expand our understanding of the diversity of planets, but also the diversity of potential life. It could shed light on theories like panspermia, the idea that life might spread from planet to planet, or even star system to star system, perhaps hitchhiking on asteroids or comets. If we find similar biochemical signatures across different star systems, it might suggest a common origin or pathway for life's genesis. The challenges, of course, are immense. Not just propulsion, but also communication across light years, protecting delicate instruments from cosmic radiation for decades and ensuring their autonomous survival. Yet the drive to know, to understand our place in the cosmic tapestry, propels us forward. Interstellar exploration is more than just a scientific endeavor. It is a profound philosophical statement. It is humanity reaching out, not just with a physical probe, but with its deepest curiosity, its enduring hope, and its unwavering spirit of discovery. It's a message to the future from our present that we dared to dream beyond the stars. And as we consider these grand voyages, these distant messages, it brings us to another fascinating question that astrobiology grapples with. If life is indeed common, and intelligence perhaps not so rare, then why haven't we heard from anyone else? This profound silence in the universe, often called the Fermi paradox, leads us to wonder about the great filter, or the possibility of hidden civilizations. But that, my dear listeners, is a thought for another quiet moment, as we continue our gentle journey into the wonders of the cosmos. As the day softly dims and the world outside begins its quiet slumber, we bring our gentle journey through astrobiology to a close. Not an ending, really, but a pause. A moment for quiet reflection under the vast, silent canvas of the night sky. Tonight, we didn't just learn about distant stars and the whispers of other worlds. We embarked on an inner voyage, guided by humanity's oldest, most profound question. Are we alone? We've traced the delicate threads of possibility, not with hurried steps, but with the quiet contemplation of a stargazer watching a meteor shower. Each fleeting light, a thought, a wonder, a moment of profound cosmic connection. Remember, this journey of astrobiology isn't about definitive answers found in a rush. No, it's a patient, ongoing conversation between us and the universe. It's a quiet whisper of curiosity that has resonated across generations, a longing to understand our place in this immense, beautiful tapestry of existence. We've spoken of looking, of searching, of extending our gentle gaze out beyond our familiar blue home. We've pondered what life might need, what subtle signs it might leave, how resilient and ingenious it could be wherever it might choose to blossom. We haven't needed to gather new facts or rush through a list of discoveries tonight. Instead, we've simply allowed our minds to wander, like a tiny spacecraft drifting peacefully through the cosmic ocean, exploring the gentle contours of what might be. We've thought about the silent expanses of the universe, the countless suns, the untold planets, each a potential stage for life's intricate dance. And in doing so, we've perhaps felt a little smaller, yes, but also immensely more connected, more deeply woven into the fabric of something grander than we can fully comprehend. This quiet search, this gentle questioning, has taken us to the edges of our imagination. We've considered the possibility of life in environments vastly different from our own, stretching our understanding of what it means to be alive. We've imagined the tiny, resilient creatures clinging to icy moons, or thriving in the swirling clouds of distant gas giants. These aren't just scientific theories. They are lullabies of possibility, sung by the universe itself, inviting us to dream of what lies beyond. And as we've explored these possibilities, we've also gently turned our gaze back to our own Earth, this precious, vibrant jewel. The very act of looking elsewhere helps us appreciate the astonishing miracle that is life right here, under our feet, in the air we breathe, in the beating of our own hearts. Astrobiology, in its quiet way, reminds us of the delicate balance, the intricate harmony, the profound uniqueness of our home in this vast, silent cosmos. So as your eyelids grow heavy and the stars begin to twinkle faintly through the window of your dreams, carry this quiet wonder with you. The questions of astrobiology are not urgent demands, but gentle invitations to contemplate, to reflect, to allow your imagination to spread its wings and soar among the nebulae. The search for life beyond Earth isn't just a scientific endeavor. It's a testament to the enduring human spirit, our unshakable desire to connect, to understand, to be part of something infinite. This journey, this peaceful exploration of what might be, doesn't end when your eyes close. No, it simply transforms. In the quiet realm of sleep, your mind can continue to drift among the stars, to softly ponder the vastness, to gently imagine the countless possibilities that the universe holds. The questions will remain, like distant starlight, patiently awaiting the dawn of new understanding. Rest now, dear listener. Let the gentle current of your dreams carry you through cosmic oceans, past silent planets, under the watchful gaze of a million distant suns. The universe is vast, full of wonder, and it cradles us all in its silent, peaceful embrace. Good night, and may your dreams be filled with the quiet magic of the cosmos. Sleep well,